Welcome everyone. In this video, we are going to talk about the diode behavior. We are going to explain how the diode behaves when is in the forward bias, how its current and voltage are related, and why we often use sometimes called the constant drop model in the circuit analysis. I will also show you how to read the most important information from the diode datasheet so we could know everything about the diode. Now, let's first start with the diode symbol. This symbol is the general symbol for the diode using in an electrical circuit schematic. Okay, every diode has an anode and a cathode. Okay, we call the positive side anode, the P side, the positively doped semiconductor as anode. So here is anode. And the negative doped semiconductor called cathode. Okay. In the schematic, cathode is shown by a line on the symbol. Now, there are some different symbols for the different type of diodes, but they generally have the same shape, a little bit difference to make sure that we distinguish those different type of those diodes. Now, inside the diode, we have two type of semiconductor that are connected to each other, a p-type and an n-type. Between those p-type and n-type in this connection, there is a region that we call it depletion region. Okay, this depletion region basically do not allow in a default setting do not allows the charges to go from the uh, P semiconductor to the N semiconductor and vice versa. Okay, so now in a diode, when we apply a forward bias voltage, okay, what we mean by forward bias? Uh, it means when we connect the anode to the higher voltage and the cathode to the lower voltage, this we call it a forward bias. Okay, the electrical field across this semiconductor applied to this semiconductor would make that depletion region smaller and smaller as you increase the difference of the voltage between the two terminals of the diode. This depletion region gets smaller and smaller. When it gets small enough, then charges could jump over this depletion region from P to N semiconductor. Okay. Now, in reverse bias, which we connect the anode to the lower potential and the cathode to the higher potential, this electrical field, this reverse direction of electrical field, would actually increases the width of the depletion region. So it makes it harder and harder to charges to go from the N semiconductor to the P semiconductor. Okay, so as you can imagine, that means when we are in a forward bias, the diode allows the charges to move through the component, meaning we are going to have a current. And when we are in a reverse bias, it resists the movement of the charge. So it means that we are cutting the current and we do not allow a conduction of current through the component. Okay. Now we mentioned that by applying the forward bias, we need to increase the voltage across the diode until the depletion region is small enough so the charge could jump. What that means? That means is not like any positive voltage across the diode would create the condition for the charges to be able to conduct through the component. We have to exceed a certain level of the voltage. So now we our component physically allows the charges to pass through. Okay, we call that voltage, that minimum voltage, okay, voltage on. Okay, this is the minimum voltage that we need to apply in a forward bias over across the diode, so the depletion region is thin enough that the charges can move from the P semiconductor to the N semiconductor. Okay, now this is the general meaning of the forward bias and reverse bias of the diodes. Now, we have normally two types of semiconductor. One is silicon-based, another one is germanium-based. Normally, silicon-based diode has the voltage on equal to 0.7 volt. So after 0.7 volt, you start conducting. Germanium has 0.3 volt. Okay, so the threshold for starting to conduct a current for germanium is lower than the silicon. Okay, now we said when we apply the voltage, the forward bias, the current will start conducting, but we need to get to the voltage on and then it will start conducting the current. But it's not like that sharp in reality as it sounds. So it's not like we apply a certain voltage and as soon as we get to the 0.7, now we have zero resistance against the current and it sharply go on. Okay, now in reality, as you can see in the chart, this is the IV characteristic of a diode. So the current against voltage. Okay, we have some sort of exponential function that defines the relationship of the current and the voltage. Now, this N is the ideality factor, okay, defined in the datasheet. And this VT is a thermal voltage, normally 26 millivolts, okay? So, and it's also included in the datasheet of the diodes, okay? And this is the actual real relation between the current and voltage, the function of this exponential curve, okay? Now, in the signal analysis, in the circuit analysis, because conducting such a function and into our analysis is going to be very costly and is going to be very hard to kind of conduct the analysis. We approximated this function with a constant voltage mode, constant voltage drop model. Okay, that give us the proper approximation of how the diodes would react and what is the characteristic of the current to the voltage. Now, basically what this constant drop model says is that once we reached the voltage on, okay, we assume that the voltage across the diode remains constant. Doesn't matter how much current we are draining from the circuit. In a real curve, if we drain more current, the voltage across the diode will also increase. But we are gonna neglect that exponential curve and we say, okay, it doesn't matter how much current we get, okay, we consider the voltage across the diode to be constant. And it is, as you can see in the graph, it's constant and equal to the voltage on. What that means? That means, excuse me, if we have like a silicon-based diode, okay, in the circuit, we replace the diode when it's in forward bias. Okay, when it is in forward bias, we replace it by a single 0.7 volt voltage drop, like a DC voltage drop, equal to the on, and it's just germanium. That 0.7 become 0.3. Okay, so in a forward bias, if you have a diode in your circuit, just replace it with a DC voltage offset or voltage drop, okay, and you're good to go for with the analysis. If it's in the reverse bias, that means there is no current, so it's open circuit. Okay, now we talked about the reverse bias, but let's look at it a little bit with more detail. Reverse bias means we have lower potential connected to the anode and the higher potential connected to the cathode. Okay, so the voltage is in reverse polarity. Okay, when it is in a reverse polarity, the depletion mode, the depletion region, as we said, is going to be increased, meaning there is less chance of any kind of charge to pass through the diode. Okay, so when we have a reverse voltage, our current going through the diode is approximately zero. Why we say approximately zero? Because in reality, we always have some leakage. As you can see, the curve is not exactly on a zero. There is a little bit of the leakage. It's very small. So if it's you're not working with a very sensitive equipment, you don't need to even consider that. Okay, but it's not like you can apply a reverse voltage as big as you want. Okay, and you have the diode to withstand against the current. No, it's still a physical component. So if you increase a voltage after a certain threshold, it's gonna burn out. Okay, and in a correct terminology, we are gonna reach the breakdown voltage breakdown. And after we reach that, this is burnout. So there is no diode anymore. So it will start conducting the current. Okay. Now, this is the general concept of the diode. Now, there are several important data in the datasheet that you always need to remember to pay attention to, and they are actually making your design calibrated. Okay, now one is voltage RRM, which is the maximum reverse voltage, that break voltage. Okay, you know it's very important. So it's the max of reverse voltage. Another one is a maximum continuous forward current. Now let's talk about that. This diode is still a physical component. So there is a limit of a current that it could conduct through it. Okay, so after a certain amount of current, it gets saturated. There is no capacity to move charges after a certain threshold. So we have a maximum current that we actually can in reality conduct through this diode. That one is shown by IF. So it's max of continuous forward current. Okay. The third most important characteristics that we need to pay attention when we read the datasheet is IFSM. Now, this is the peak, okay, the peak surge forward current. What that means, this one is continuous, so it's a steady state. This one is a surge. That means something happened in your circuit, either is a fault or a switching, that creates a transient. So there is a pulse propagating through your system. Okay, it is going to be the voltage of that pulse or the current of that pulse going to be higher than the steady state current. Okay, but we have a certain kind of like tolerance when we talk about the physical component. So every component can tolerate a certain amount of surge current or surge voltage. If we pass that, it would break down the deflection region and it burn out. Okay, so this IFSM is the peak surge current, transient current, the pulse current that we can tolerate when we are in a forward bias. Okay, now normally, like in our experiment, we work with a diode model of 1N 4007. We normally use that. Okay, for this diode, if you read the data sheet, normally the max reverse voltage is about 1 kilovolt. Okay, so let me mention that. So this one is normally typically is around 1 kilovolt. The maximum continuous forward current is normally about 1 amp. Okay, and the peak surge forward current is normally around like 30 amp. Okay, so basically before building any circuit, you must check those diodes characteristics. Okay, this is the tolerance of those diodes. We never design only for continuous operation. We have to consider the transient kind of like events like surge. Now, to summarize, the diode conducts significantly only when it's in forward bias and it's above the voltage on threshold. Its current rises exponentially, okay, after that on point, okay, but for most practical circuit, we assume a constant voltage across that diode. In a silicon, it was 0.7 volt. In a germanium, it was 0.3 volt. Now, you have to always check the datasheet for maximum rating before building your circuit. Now, after this, we are going to go through some simulation to simulate the IV curve and plot it so we could confirm is actually is exponential function. Okay, let's move on to the simulation part. We are going to use multisim to plot the current voltage, as we call it, IV characteristic of the diode. And I don't want to assume you have like a experience working with a multisim, so we are going to go step by step. So even if you have never used multisim before, you will be able to follow along with, by simply doing exactly what I do. Now, a reminder. Remember that we expect that the diode to conduct very little current until we are around the voltage on. We are going to use that specific model that we mentioned. So it's silicon based. The voltage on is going to be 0.7 volts. After that, the current rises exponentially. So we are going to see that in simulation. Now, step one, when you open your multisim, you are going to see a blank page. It's a workspace. Okay. So first thing to do is to create a new schematic. Now, the new bottom is all over the page. Okay. So there is one here, one here, one here, and one in the file menu. Okay. So we click on the new, we use blank, create the project. Now we have a blank schematic. After that, now we have to actually place the component that we want to have in our circuit. Now, in our circuit, we need a diode, we need a voltage supply, okay, and we need a ground because every circuit needs a reference point. Now, Where to find them? You can see there are several categories that is mostly used here in the menu. But another place to find that components is under the menu place. You have an option named component. You click on it. It's open up all the database that the multisim has. Now, in the group, scroll down, we wanted to have a diode. So we choose the diode category. We choose a diode category. Now it's open up several family of the diodes. We mentioned earlier that we have several different diodes. Now we want the regular one. So we click on the diode. Okay. Now we wanted to look for a specific model. The model that we wanted to use is what was 1N4007. So we are going to look for it. 1N4007 here. Okay, this is the family model of those. We choose the general model, the one that says 1N4007G. We click OK. Now you can place your component. Now, the next component that we want was a DC source. So we are going to go to the category source in the groups. Now, the families of the source that we have, we want power supply. So it's power source. And we want a component DC power. Okay, so we choose that. Click OK. Now we can add our power source. And we said next one is ground. Now, ground is on the same category in the groups, in the source group. In the power source, you can see the ground. You click OK, and you place your ground. Now we are all done. We don't need any category, so we close the component page. Now, we need to connect them, so we have the circuit. To connect them, you go to the terminal, left click, go to the destination terminal, left click again. We are going to do the same for other component. And as we said, we want to connect the ground, so we have a reference point. So we are going to connecting a ground to the lower potential of our source. Now our circuit is complete. We want to observe voltage characteristics against current. So we need a meter. So what we are going to do is we are going to add a current probe. You can see all of them probe here. We are going to choose the current probe, and we are going to put it in series with the diode because we wanted to like analyze the current going through the diode. Now, in order to get the analysis done, we are going to go to the simulate menu. There is an option named analysis and simulation. We are going to click on that, open up a page. It's open up a page. Now, what we wanted to do is we wanted to like sweep the DC voltage and see what type of current we would see. So it's going to be a DC sweep. Okay, we are going to choose our source. We have one source, so it's going to be V1. Okay, this is one source in the circuit. If you have multiple source, you have multiple options that you have to choose between them. Now, we are going to start. We wanted to always, we just wanted to like check the forward bias in this example. So the starting value would be 0. And we are going to have like a stop value 1, or let's say 2. Okay, doesn't matter. And we want to have the step defined based on what accuracy we want. As much as you lower the step, it means you have more accurate, but you have more computation burden. Okay, so we run that. This is the setting. Now we click run. Okay, when you click run, it would create that IV curve. that you see. Okay, now in this part, let's talk about the minimum series resistor that we need. Now, what that means. In any electrical circuit, as we said when we talk about the data sheet of the components, or data sheet of a diode component, we said there is a maximum current that component can conduct. We never wanted to reach that maximum safe current. Exceeding that is far worse than that. So if we are, even in the worst case scenario, we don't want to reach and get near that safe current. Now, how we can control that by limiting the amount of current in our loop or in our circuit. The way that we do it is by using a resistance. So normally for current limiting purposes, we use a resistance. So now we need to provide a resistance, which we call it a safe resistance. Okay, so we could make sure that our current remains below and far away that maximum current in the datasheet. Now, you can see the circuit here that we have a voltage source. In our example, is that 10 volt. 10 volt. We have a diode, and as we said, we wanted to limit the current going through the diode using a resistor. Okay, which we call it our safe. Okay, now how we could calculate that? Let's go through that. Now, we have a circuit, and we know one of the fundamental tools in a circuit analysis is the KVL. So let's run a KVL through this circuit. If we run a KVL, and by the way, this is the way you can run KVL. We start at this point. We identify the higher potential, lower potential of each individual component. So this is lower, this is higher. In the resistance, we consider the current going from left to right. So this is going to be positive, higher voltage. This is going to be negative, lower voltage. This is going to be higher voltage. This is going to be negative, lower voltage. Now, when you do the KVL, we start at this point. We move up. When we go through the component, whatever polarity that we exiting the component is going to be the polarity of that parameter in our equation. So this is plus voltage of the source. Then we move on. This is minus voltage over resistance and minus voltage over the diode. And then we are in our initial point, so it's all equal to 0. That's a KVL. What that means? That means our VS, this is our KVL. Okay, now what is VR? We know this is Ohm law. VR is actually the resistance times the current passing through this resistance. So this is the amount of voltage we have across the resistor. What is Vs? We know it's a 10 volt, so it's 10. Correct? What is Vd? We said we use a constant voltage drop for modeling the diode. So this specific diode that we used is a silicon-based diode. So V on is 0.7 volt. We are going to implement that. So it's going to be 0.7 volt and all equal to 0. Correct? Now, we want to limit the current to the maximum current. These two are constant. So what limits that? As much as we increase the resistance, the current goes lower. Worst case scenario, the boundary is that current is a max current. Okay, so that means this is gonna be the minimum resistance we need. So worst case scenario, we do not exceed the max current. Okay, so what would be the minimum resistance here using this formula? The R minimum is gonna be those voltages, okay, those voltages that we have. So it's gonna be V source minus VD divided by maximum current. Now, for this specific example, when we wanted to consider a model 1N4000, the one that we simulated earlier, 1N4007, okay, the maximum current is 100 milliamp. Okay, so here we consider the maximum current 100 milliamp, which in the formula you have to put the amp, so it's going to be 0.1 amp. Our Vs is 10 volt and our Vd is 0.7 volt. So the minimum, is it? No, I'm going outside of the board. The minimum R become from all of these become equal to, okay, doing those math, it become equal to 93 ohm. You can do the math. Okay, now we are not done. We said we are not even wanted to get near the Imax. This value is, if we put that, we are gonna get in a certain situation, we are gonna get equal to Imax. We don't want to get even near that value. So we are gonna apply a safety factor. For this example, we are gonna apply like a 10 as a safety factor. What that means? That means we are consider our safe resistance as 10 times of our minimum resistance, which is what? 930 ohm, close to 1K. Okay, so that way, by using that safe R, okay, we can make sure that we never even get near our maximum current. So let's summarize. We use the formula to calculate the minimum resistance value that we need to protect the diode based on the supply voltage. Now, the diode is also forward biased, so we have a forward voltage drop for the diode. And we consider the worst case scenario, which is the maximum current rating for that diode. After that, we multiply that value by a safety factor. We consider 10 as a safety factor for extra protection. Okay, which our result get 930 ohm, close to 1 kilo ohm. Okay, now in next step, we are going to simulate the same circuit to see what's going to be the value of the current if we have approximately this amount, like 1 kilo ohm of resistance in series with the diode, and what amount of current we are going to get. Okay, and we see if it's higher than 100 milliamp that we said, or it's lower than 100 milliamps. Okay, so this is going to be our next step. Okay, let's do the Simulink, do the simulation through the multisim. So we see if our resistance that we calculated is actually limiting the current below the maximum current. Now, in order to save times, I'm going to use the previous circuit that we make and modify it so we could have our new circuit. Now, I am going to delete this connection. Let's Move this out of way, and we are gonna add a resistance. So in menu place, component, resistance is under the basic components. We want resistance. Where is the resistance? Here, resistors. Okay, and we said it's gonna be around 1K. You can see 131, but I'm gonna be more conservative and choose 1K and put it here. We are done. Let's connect our circuit. And also, we need to change our voltage. We consider 10 volt as our voltage. So if you double click, it will open up and you can change the settings. Now we have our basically circuit. So what we wanted to like actually uh, uh, see the current. Okay, so we wanted to like first a multimeter to voltage to capture the voltage across the diode. Okay, to do that, I am gonna let's delete that one. I am gonna have a multimeter connected to this point. Why this point? Because the cathode is connected to the ground, so it's always zero. If I measure this value, that means I have the voltage across the diode. Okay, now let's do the simulation. We are gonna click run. Okay, and we are gonna see this is our voltage. What is the value of voltage? Let's zoom in. This point. See, is near the we are okay. Let's do the simulation. In order to save some time, I already developed the circuit. So for adding the resistor, we have to go to the place to the component option. Here in the basic category, you have the resistor family, and you can choose your value, which I choose 1K to be more conservative. Our value was 930 ohm. You can choose like 976 or 953, but having the tolerance in our circuit, and it's not like the resistor has have their nominal values. So we are going to be a little bit more conservative. So we are gonna connect the 1K to our circuit, and before we had 12 volts. So if you double click on the component, you can change the setting. I set it to the 10 volt because our calculation was based on 10 volt. And I put a amp meter in series with the diode because I want to see what is the current when I have 1 kilo ohm resistance in series with the diode. And I wanted to like also observe the voltage across the diode. I put a voltmeter here. And since the cathode is connected to the ground is always zero, so the voltage here is going to be the voltage across the diode. Now, we go to this simulate. In previous setting, we set the simulate to DC sweep. You need to change it. Otherwise, it would change. It would keep that. So we wanted to like have a DC operating point. Okay, we don't sweep anymore. You choose the DC operating point. You save it. If you don't do that, it would go with the latest kind of like setting that you had. We save that. We click run. Okay, when we click run, it would give us the value of the current and the voltage across the diode. You can see the voltage across the diode is 600 and around 660 millivolt, which is 0.66, very close to the 0.7 that we assumed. Okay, and the value of the current is 9.34 milliamp, which is, as you remember, we consider a 10 times correction factor. So our original Imax was 100 milliamp. Considering the 10 times correction factor is going to be 10 milliamp, and you can see that we are on 9.34 milliamp. So our design is perfect, and simulation would actually prove and validate the theoretical calculation that we had. Okay, now that we run the simulation and the theoretical calculation, let's work with the actual circuit in the lab. Now, to do that, we need a breadboard, okay? And we need to place all the components into our breadboard. Now, this is a typical breadboard. You see a lot of ports on it, okay? We have two positive rail, one at the bottom, another one at the top, and two negative rail, again, one at the bottom, one at the top. Each rail, each horizontal rail are connected to each other, same as the positive one, same as the positive one here and the negative one here. Now, the middle one, okay, are connected vertically. So each column here is connected to each other. Also, each column here is connected to each other, but individual columns are not connected to each other. Now, for our system, for our circuit, we wanted a series of voltage source, resistance, and a diode. So as you can see, we have a diode, a resistance, and I connected the plus and minus volt for the source, and basically create the loop that we had in our simulation and in our calculation. Now, the diode, let me show you a little bit more closer. We said the diode has an anode, come on, I hope it gets, you can see the actual diode. Yeah, the diode has two terminals, anode and cathode. You see one of them has a black band marked on it. That one, like here is the bottom one. That black band means cathode. So the other one is anode. The black one is cathode. Okay, so when you want to like do the forward bias, you need to pay attention to those connections. Now let me connect my system back again. Okay, and I broke my jumper. So let me replace it in another jumper. Okay, now I have my closed circuit. Okay, now before I start the circuit, I wanted to make sure I chose the 1 kilo ohm resistance based on the color codes on the resistance. Okay, but I want to make sure that is actually 1 kilo. So I'm going to use the multimeter. You can see the probe here. We have the common probe, which is the black coded. We connect the common probe. We have three measurement probe. One is used for volt and ohm. The other two is for amp, but different range. One is the amp range, another one is milliamp and microamp range. Okay, now we wanted to like first see if our 1 kilo ohm is actually 1 kilo ohm or how much tolerance it has. So I'm gonna connect my measurement probe to the socket dedicated for ohm meter. I'm gonna turn on my multimeter and put it on the ohm setting. Okay, and I'm gonna choose the range. I'm expecting a 1 kilo ohm, so I'm gonna change the range. You can see here there is a range. I'm gonna change the range to the kilo ohm. Are we good? Because I'm expecting a kilo ohm range value. Now, I'm going to put it down and connect the two probes, these two probes, across my resistance. So one here, another one here. And as you can see here, that my multimeter reads that resistance equal to 0.9983 kilo. So it's not exactly 1 kilo. It's actually 983 ohm. Okay, so there is a tolerance. So it's if you remember, our safe was 930. So it's good that I've been conservative and I choose the 1 kilo ohm, because even though there is a tolerance, I'm still above that safe resistance. Now, one thing that to remember, always remember, when you wanted to like measure the resistance, there should be no source connected to your circuit. So the circuit is de-energized. Otherwise, it would affect your measurement. Okay, now let's go for the test. What we want to do is we wanted to like apply the 10-volt voltage that we had in our simulation and in our simulation and in our calculation. So we need first a measuring point and then the supply voltage. Now, let's first start by measuring point. So, because remember, last thing that you connect to your board and apply to your board is the source. Okay, and when you wanna to like end the measurement, first thing that you disconnect is also the source. Okay, that's a safety protocol. So remember that. Now, we want to first, let's calculate or measure the voltage across the diode, because we know that theoretically it should be 0.7. Our simulation showed 0.66. Now I want to see what the measurement tells me. I want to have a DC voltage meter. So it's the same probe, because the measuring probe of ohm and volt are the same, and we don't change the common probe. So we are gonna set the value to volt, okay, DC volt, and it's gonna be in a 1 volt range, so we don't need to change the range. But if you need, do that. And we wanted to like calculate or measure, the voltage across the diode. So I'm gonna connect my probes across the diode. Please don't get disconnected. Help me. Okay. Now I am gonna connect my DC source. And remember, we are gonna do the forward bias, so polarity is important. So I'm gonna connect the negative port of the DC source, where is that negative port of the DC source, to negative port of my circuit, and the positive one to the positive port of my circuit. Okay, now before I apply that, actually let's set the voltage and then apply this. Now we are gonna turn on our voltmeter, our DC supply. It is already set at 10 volt, but if you wanted to change it, there is a knob that you can change the voltage. Okay, so we wanted a 10 volt, so we are gonna stay at 10 volt. Are we good? Now we are gonna apply our voltage to our circuit. Okay, now our circuit is energized, and we are measuring the voltage across the diode. See what the measurement says? It's 0.78. Theory says 0.7, simulation says 0.66, but the measurement says 0.78. Okay, now see, there is a difference between the theory, simulation, and measurement. there are a lot of things that plays a part into that error. One is the physical kind of like errors in a diode itself, because manufacturer cannot build an ideal component. The next part is the error in our measurement device. That multimeter also has error. We have electromagnetic interference because we have a long probe. Okay, and also this is a DC voltage. Yes, we connect that and we set it at 10 volt, but that doesn't mean that it's actually 10 volt. There is a certain amount of error in that. Now we run that. Now we wanted to like see the current that passes through the circuit. So as I said, first thing to do is connecting the source. Now, ammeter should be connected in series with our circuit. So I need to disconnect my circuit and put my meter or my multimeter in series with my diode. Okay, then I said socket for voltmeter, the port for voltmeter and ammeter are different. So we need to change that. We are going to put our setting to the DC amp, and we have two type of range. We expect a milliamp, so I'm going to set that to the milliamp. And the milliamp port is the bottom one here. Okay, so I'm going to put my probe connected to that port. Now, one thing to pay attention is that different from the volt, milliamp, the amp and milliamp for DC and AC has the same probe. Okay, I see if I could see you. See, this is the amp, is both DC and AC. So as you can see in the picture, the default is AC. You see here, it's amp AC. You need to change it. How to change it? With that orange button, we change it to the DC. Okay, now, and the range is milli, we want milli, so we don't change the range. So now I have every connection that I need. Let's apply that 10 volt voltage. Okay, what I read, you can see that. Let me get it closer. It's 9.442 milliamp. Okay, we were expected a 9.3 based on our calculation. Our measurement shows different number. Now our simulation, now our measurement shows 9.42, 43 something milliamp. Now our maximum current was 100 milliamp. We applied a safety factor of 10, okay, which we reached to the 10 milliamp maximum safe current. And choosing this resistance, 1K resistance, although it has a tolerance, it has the error of on his resistance, and it's actually 983 ohm instead of yet 1 kilo ohm, we're still under the maximum current that we designed. Okay, so we are good to go on this setting. Now, beside that, there is another exercise in our assignment, which is the analysis of behavior of our diode when we talk about the transient situation. Now, let's de-energize the system first. Let's disconnect the multimeter. We don't need it anymore. So turn off, go rest. Now, we need to close our circuits. Okay. And we don't need the DC voltage because we wanted to like have a transient system. To use that for the transient system, we're using the signal generator here. And what we want to do, we want to apply a step voltage. Okay, so we turned on the signal generator. Okay, it's gonna take a while. Now, until it's take a while, it takes okay, it's up. Now, for measuring the transient, we can use the multimeter. We have to use the oscilloscope. Okay. Now, I want to measure both input voltage, the input signal that I wanted to put. Okay, so I'm gonna connect my first channel to the input of my circuit, the signal generator. Let me connect that here. Input of my circuit. Okay, and remember that there is two ports on the probe. This one is common port. This one is the measurement probe. This goes to the this one is a common port. This one is the measurement. Okay, so this goes to the voltage you want to measure, or current, and the signal you want to measure. This one goes to the either the next terminal across that. Normally is under the lower potential. Okay, now what I wanted to see is how the current would react to the transient signal applied to the diode. So I wanted to measure the current, but the oscilloscope measures voltage. So I need to change the current to voltage. How I can do that? I already have a resistance that follows the Ohm law. So if I measure the voltage across the resistance, it basically means that with a certain proportion, with a certain coefficient, I'm gonna seeing the behavior of the current. Now, I wanted to just check the behavior, not the amplitude, so it's okay. I don't even care about the coefficients right now. I just wanted to see what's going to happen behavior-wise, dynamic-wise. So I'm going to connect my probe here across my resistor. Come on. Okay. Now, we said we wanted to have a transient voltage. In our assignment, we said a step voltage is square wave. Okay. So we have to choose the waveform. The default is sine. So I'm going to click on the waveform. I'm going to choose the square wave. Okay. Now I can change the frequency. I want 1 kilohertz. The default is 1 kilohertz, so I don't change it. The amplitude I want, based on the task that we want, is 0 to 9 volt. So I put 9 volts of peak. Okay. Then, but when you put 0 to 9 for a step voltage, it's actually considered from minus 4.5 to plus 4.5. So it's make a symmetry against over the 0 line. Okay, I don't want that. I want 0 to 9. So I need to set an offset to kind of bring it up, and then it would work from 0 to 9. So I'm gonna choose an offset equal to 4.5 volt DC. So now my voltage changes from 0 to 9. Okay. Now, there is a duty cycle. The default is 50%. I don't want to change that because it doesn't affect me. So I don't change it. Okay. Now, I'm going to push the output to apply this voltage across my circuit. Now, as you can see, the oscilloscope catches those waveforms. Now, you can see, if you can see, let me get it closer. If you can see, we have a certain kind of like transient happening. Let me zoom in. How I can zoom in? By changing the voltage division and time division in our circuit. So this is the channel 2 that measures my output. So I'm clicking on channel 2, and then I try to change the voltage division to zoom out. So I'm going to reduce the voltage division, meaning each of these square now have less value. Okay. For example, here now I put it in a 1 volt. Okay, so each of these squares now means 1 volt of the voltage value. Now you can see the transient better. Okay, what I want to do is to see how long it would take the diode. So after we turn off the voltage, so we disconnect the forward bias, the current goes to 0, because it's not like an instant move. It's a physical system, so we can't just disconnect the current instantly. There is a gradual decrease in the current until it gets to 0. Okay, that's the transient here. Now, to show that, I'm going to increase the time division, okay, so you can see what I mean by transients. Okay, the diode tries to make the current 0, but it cannot do that instantly. Now, that time that we define is the time when the input signal gets disconnected, gets to 0, that edge, until we stabilize at 0 line. Okay, we stabilize at 0 line. Now, if you look at it, which I hope is clear, it takes 2 of those square until we get to a certain kind of like tolerance, and the error is so small that we can say, okay, we are now settling at 0. It takes 2 of a square. Okay, now in the time division, I put the time division right now at 500 nanosecond. Okay, we have 2 square, which means 1000 nanosecond or 1 microsecond. So the time that this specific diode needs to gradually decrease the current until it's disconnect the whole current is 1 microsecond. Okay, so by this experiment, first we learn how the diode reacts to the DC voltage. Okay, we tested our safe resistance. We tested the voltage drop against the diode, so we know if it's accurate enough or how far is off from the theory. Okay, and then we apply a dynamic input to see what is the transient behavior, a dynamic behavior of diode when we have a change in a state of the input. So the voltage goes from the forward bias to reverse bias. Okay, so that's about it so far. Let's move on to the next exercise. Okay, let's talk about the LEDs and how the LED would behave. In this part, we will study how an LED behaves when we vary the current through it using a potentiometer. And we will build a circuit that includes a resistor, a potentiometer, an LED, and a 12-volt DC power source. But first, let me explain the circuit and why each component is important, especially why we need the resistor to limit the current. Now, you can see the circuit here, the circuit that we have a voltage source, we have a resistor, we have our potentiometer, and we have our LED. Okay, and they are connected in series. Based on our design, our voltage is 12 volt, the source is 12 volt. There is the series resistance is 1.5 kilo ohm. The potentiometer could be the max of the potentiometer is also 1.5 kilo ohm, and we have an LED connected to our system. Now, when you talk about the LED, we need to label the LED properly. We have anode, okay, and we have cathode. We already talked about that when we talk about the LED. The one with the line is cathode. Okay, now you can see the symbol is different from the generic diode. LED has these two flashes on the symbol, so you could distinguish the LED from the regular general diode. Now, why we have these components? This is the schematic of our circuit. Okay, the positive terminal of the 12 volt DC power source connects to a 1.5 kilo ohm resistor. This resistor is also connected in series with a potentiometer, which allows us to change the total resistance manually. And finally, the current flows through the LED here, okay, before returning to the negative terminal of the power supply. Now, it is very important to connect the LED with the correct polarity. So we have two terminals. When you look at the LED, okay, we're going to talk about it again when we want to run the test. But when you look at the LED, one of the legs are longer than the other. So the longer leg is the anode, and it will go toward the higher potential or a positive terminal. Okay, the shorter leg is cathode, which connect to the lower potential, or in this case, ground, and we need a ground to make sure we have a reference. Now, if you connect the LED in a reverse kind of like connection, then it would not light up because the LED would be in reverse bias, and it's only emitting light if it's in the forward bias, meaning there is a current passing through the LED. Now, the resistor and the potentiometer together control the current that flows through the LED. Without those resistors, LED would try to draw as much as current as it can based on the power supply that we connect to them, which in reality would instantly burn out. Okay, so the total current through the LED is given by the formula that we had that says this is a KVL. Okay, and the formula says when you run a KVL, you have Vs minus R, let's say this is R1, this is R2. The potentiometer is R2. R1 times current minus R2 times current, okay, minus the voltage across the LED, and it's equal to 0. Okay, so based on that, you can calculate that our current is going to be our volt source minus the voltage across the LED, okay, divided by the total R, which is R1 plus R2. R2 is variable, okay, is a potentiometer. So that's give us how much a current is passing through our circuit. Now, LEDs have different voltage drop, okay? Before we said that the generic diode, the silicon one has 0.7 and the germanium one has 0.3 voltage drop across it. The LED has 2 volts. voltage drop across it. Okay, so remember that. Approximately 2 volt is not exactly 2 volt. Now, this is very important. And a standard LED are safe only when the current goes to maximum 20 milliamp. Okay, so that's why we include that 1.5 kilo ohm resistor as a fixed current limiter. So even if the potentiometer in our circuit is at zero, okay, and is has a very small value, we are still under and conservatively far from that 20 milliamp. Okay, now that we understand how this circuit works and why we have the resistor as an essential component, in this step, we will kind of like simulate the circuit in a multisim and change the potentiometer and plot how the current would change as we adjust the resistance. After that, we are going to build that on a breadboard and observe the brightness of the LED at different resistance. Let's go over the simulation of that circuit that we described in the previous part. As you can see, we have a circuit with a 12 volt DC source. We add a 1.5 kilo ohm resistance in series with that source. Then there is a 1.5 kilo ohm potentiometer, and it's connected to an LED, which after that we close the loop and circuit. Now, we set all those values, the voltage. If you double click, you can change the value. So same goes for the resistor and potentiometer. And we need to set the on current of LED, is the minimum current that it needs to light on. We set it as a 2 milliamp. Okay, the default is 5, so you need to change it if you want it to turn on properly. Now, we want to measure the current that passed through the LED, and we also wanted to measure what is the voltage across the LED. Okay, now in potentiometer, remember the percentage is the amount of resistance that is out of use. So when it's 0%, that means the whole 1.5K is in the circuit. Now, see, when we run in a 0%, the value of the amp is 3.34 milliamp. Okay, and the voltage across the diode is 1.99. We expect it to be 2 volt, but it's very close. Now, we stop the simulation. We set it to the 50%, and run it again. Now you can see that because we eliminate 50% of the potentiometer from the circuit, the current raises to 4.44 milliamp, and the voltage across the diode goes beyond 2, so increases, and it becomes 2.01 volt. Now you can see when I simulate that, the LED would light up. Okay, let's stop. We go to the 100%. Okay, so now we don't have any resistance here. It's 0. Let's run the simulation, and you see again the value of the current increases to 6.64 milliamp, and the voltage across the diode also increases to the 2.04 volt. Okay, so basically you see that how we can build and simulate the LED potentiometer circuit. And in this example, we measure the diode voltage and current at different setting for potentiometer, and observed how adjusting the resistance changes the LED's brightness, which in this simulation, we show it by the current going through the LED. And now in next step, we are going to build the same circuit on a real breadboard and verify the result in an experiment. Okay, now that we went through the simulation and the theory, let's talk about the actual experiment. Now, as you can see here, I already implemented the circuit that we need to have, like the same circuit that we had for the simulation and the theoretical explanation that we had. We have a 1.5K resistance, so I didn't have 1.5K, so I used, as you can see, two resistor, 1 kilo ohm and 500 ohm in series, so I could create that 1.5 kilo ohm. That was the safe resistance for our diode, okay, for the LED. So you don't, if you don't have these values, it's better to go higher than lower, okay? So we wanted to make sure that our current do not exceed the maximum current that we intended. Now, as you can see, we have that resistance in series with our potential met, and then in series with the LED and all the way back to the source. Now, one thing is important that to notice, LEDs, as you can see, had two terminals. One is longer than the other. Okay, the longer one is the anode. Okay, is the positive terminal. So you need to, if you wanted to like do the forward bias, you need to connect the longer terminal into the higher potential. Now let me put it back where it was. Come on. Work with me. Okay. Now, before again I start, I wanted to make sure that I know the situation with my potentiomet. So let's talk about the potentiomet. Potentiomet had three terminal. Okay, the two left and right terminal basically is the whole resistance is connected to the two points of the whole resistance. The middle one is the terminal that sweeps through the resistance. So if you wanted to like change the resistance and sweep, you need to connect the circuit between one of these side terminals and the middle one. Now, before we start, let's see what is the situation, what is the value of our potentiometer. So we know what we are dealing with. I'm going to turn on my multimeter. I hope you can see it. Is that? Okay. Again, I'm expecting around 1K, in the range of 1K. So I'm going to change the range to the kilo. Now, I'm going to connect one of the probes to the one of the side terminals and the other one to the middle terminal. It's a little bit tricky because it's a very kind of like small component. Now, as you see right now, I am in a zero ohm. So I am all the way out of the resistance. So I am gonna now try to turn the potentiometer. And as you can see, now I am increasing the resistance. So let's go all the way through. So this is a 1 kilo ohm potentiometer. Okay. Now I wanted to like have, based on my assignment, I want to have 0%, 50%, and 100%. So 50% is gonna be 500 ohm. So I wanted to like see where is the 500 ohm. So when I wanted to like set it, I am good enough. Good know that where should the pin be? Go ahead, 500, 1. Okay, that's good enough. Okay, exactly 500. Okay, now see there is a. Let me show you exactly. One side of the pin is flat. Okay, so I can mark that. Okay, if my flat indicator is all the way horizontal, that means 50%. So now I know what to expect when I wanted to like set that in a 50% value. Now let's put it back into the circuit. That was here. The middle one was connected to the LED, and the right one is in series with my, let's make it a little bit more accessible. But now my circuit is all the way through. Now, before I start measuring the current, okay, I want to see what is the voltage across the diode. Okay, so I'm gonna put this multimeter in DC volt. I am gonna connect my probes across the diode, the LED. Now, our source is 12 volts DC in our circuit, so I'm gonna connect them, connect the inputs to the source, the DC source. Now, be careful to connect the minus terminal to the negative terminal to the negative rail, and the plus terminal to the plus rail. Now that everything is okay, I'm gonna turn on my circuit, and now why is not working? Let me see if I have any disconnection, which is, oh yeah, here. I am disconnected. The pins are in the wrong port. So I am gonna connect them properly. And this is gonna be that one. So this is my circuit. This is and my circuit. This one is good. This one is in series and all the way. Let's see. Okay, now it's working. Now I want to see the voltage across the diode, so I'm gonna connect the voltmeter across the diode, and as you can see, can you see? Yeah, there is 2.39 volt across the diode. So theoretically, we consider that as a 2 volt. Close enough, there is a error in our measurement and the component, so we know that. So let's we consider that as the measurement of voltage across the diode. So you can calculate even the error and recalculate the current that you theoretically estimated that passed through the diode. Now, we want to measure the current, so let's turn off our circuit. So we know that the current
meter should be in series with our component. So I'm going to add another socket. So now I can put in series, put the ampere meter in series. Now I'm expecting a milliamp range, and let's put that in the milliamp range and connect this probe to the milliamp socket. Now it's still AC, so I need to change it to the DC. So now milliamp DC, and we are going to connect the amp meter in series with our circuit. Now, I didn't change that potentiometer to the from the 50%. So whatever we see is for 50% value of our potentiometer. Let's connect the circuit, the source. Now, as you can see, in 50%, we have 4.6869 milliamp of current. Okay, 68. It's closer to 68. 68 milliamp of current. I don't think you can see that. Oh, now it's good. So it's 4. See, it's changed. That's the errors easily could change. You can be you have to be very careful about that. 65 milliamp. Now, I am gonna change the value of the potentiometer, and please look at the. Let me bring it a little bit up. Look at the brightness. I hope you can see that. Is that okay? The brightness of my LED. Now let's change it. Now I'm all the way up for down for our resistance. Okay, so it's 0% resistance in potentiometers, and my ammeter reads 6.08 milliamp. And now look at the brightness when I go to the 100%. It is getting lower and lower. I hope you can recognize that. The change in the brightness is a little bit hard to show it in the video. But when I go to the 100%, okay, of the potentiometer, resistance in potentiometer, my ammeter reads 3.75 milliamp. Okay, so you can see that by changing the resistance, the current through the LED would change, and since the current is changing, the brightness of LED also would change. So this is show us the behavior of that LED. Let's move to the next exercise. Okay, let's move on to the exercise 4, which is about the Zener diode. In this part, we will design a basic voltage regulator circuit using a Zener diode, and the goal is to keep the output voltage constant, even if the load or input changes slightly. We will design the circuit and understand the role of the Zener diode, and also calculate the value of the resistor that we need to limit the current so we have a safe level. Before we start, let's talk about the Zener diode. Now, as you can see, the symbol for Zener diode is a little bit different with the symbol of the general diode. We have somehow letter Z at the end of the flash symbol. So this is the symbol for the Zener diode in an electrical circuit schematic. Now, Zener diode and its application is different from the regular diode. Regular diode, we said we wanted to use it in a forward bias, okay? But Zener diode, because of its characteristics and because it's used to have a constant voltage, we normally use it in a reverse bias. But not only reverse bias, we normally use it in the region of the voltage breakdown.
Okay, we already said that the breakdown voltage is a dangerous voltage for regular diode, but in Zener diode, because of the physical characteristics, we are gonna work on the break voltage, which we call it Zener voltage. Okay, but in order to not burn out our component, we need to limit the current passing through the Zener diode. What that means? That means we have an I max, and to be safe. Okay, so we don't want to like burn out our diode and put it in the excessive stress, current stress. So we are gonna define an I max, and we are gonna use a resistance in our circuit, so we make sure that we are within the safe region. Now, as you can see, the curve of reverse bias, similar to the forward bias that we discussed, has an exponential kind of like behavior. Okay, so there is a knee here. In around the knee, because the change in the voltage in respect to the change in the current is quite much, and basically that means we don't get a constant voltage, which is the main goal of using the Zener diode. So we want to move away from this knee part, okay, and go toward the one that has like a very negligible voltage difference and is a linear characteristics. So we want to define an minimum current, and the minimum current is the current that we make sure that we already passed that exponential curve or knee in the curve that we have in IV characteristics. So the region that we wanted to like work, okay, is this region. Okay, we want to always remain in this region. So the current is between, should be between minimum current defined for the Zener and maximum current defined again for the Zener. And we are working in a reverse bias. So higher potential is going to be at this part. Oh, sorry, listen. At this part. And the lower potential is going to be in the anode. Okay, so it's the opposite way of general diode in our circuit. Now, this is a circuit for a Zener diode voltage regulator. Here we have a voltage source equal to 10 volt in our example. Okay, this is a DC source, and it's connected to a series RS. Now, this RS is the one that makes sure we are below the maximum current. So that RS is the one that limits the current so we do not pass the maximum value allowed in our IV curve. Now, we place the Zener diode, okay, in a reverse bias across our output. So the terminal A and B are our output. Okay, so this should be in a reverse bias parallel to output, across the output. Okay, so this is higher potential, this is the lower potential. As like you see, I connected to the ground, I connected the ground to the anode, and the voltage will be in the cathode. So this is reverse biased. Now, in our specific example, the Zener diode has a breakdown voltage or Zener voltage of 4.7 volt. Okay, so which means once the voltage across the Zener diode reaches the 4.7 volt, it will start conducting in reverse and clamp basically the voltage. Okay, this keeps the output voltage stable even if the input voltage or the load have a variation. Now, we already said we need a series resistor that RS, which is very important part. We must add this resistor in series with the Zener diode because without the resistor, the diode would draw excessive current, okay, and they're not. So the resistor limits the amount of the current that can flow through the Zener. Now, how we could calculate the Zener diode? Same as before, we run a KVL in our a loop that contains the RS voltage source and the Zener diode. Okay. Now, if we want to limit the current to the maximum current, that means if you do a KVL, the resistance should be voltage of the source minus voltage of the Zener diode across the Zener diode divided by maximum current. Now, the input voltage is 10. Let's write it down. We know that the input voltage, this one, is 10 volt. The Zener diode, the Zener that we chose, the voltage Zener across it, as we already said, is going to be 4.7 volt. Okay, me put the unit also. Okay, and in this example, we said we wanted to limit the current to the 25 milliamps. So the maximum current is 25 milli. Okay, now let's run the calculation and see what's going to happen. So if we plug the values into our system, basically it's going to be equal to 5.3. Is that correct? And over 0.025. Okay. Remember, it should be in amp value. So if the milliamp, if you have milliamp, you need to change it to the amp. Now, if you calculate that, that means our resistor, you do the math, it's gonna be 212 ohm. Okay, so basically we need at least 212 volt, 212 ohm in series with the diode, so we make sure that we avoiding passing the maximum current. Now, so to summarize, we use the Zener diode, okay, to build a basic voltage regulator that keeps the output fixed at the Zener voltage, which means output is gonna be always 4.7 volt, okay, and we use the formula for the safe current, for the safe resistance, to calculate the resistance value, and which we found to 212 ohms. So this resistance is very critical. Remember that it protects the diode by controlling how much current it would flow. Now, next we are going to talk about how we could simulate, and we are going to through the simulation of the same circuit in order to find out what is going to be the values of the current and how it would react if we change the load or if we change the voltage source. Okay, now that we designed a basic Zener voltage regulator and calculated the series resistor, we are going to verify the performance of that by simulation in multisim. I will walk through how basically to simulate that. As you can see, I already put the circuit and basically build a schematic in the multisim. You know that you can add all these values by in the menu place in the option component, and you can choose the category. So for the source and ground, we choose the category source. The resistors and potentiometers are in category basic, and the diodes are in the category diode. So for the Zener diode, we use the 1N4732A, which has the 4.7 voltage, Zener voltage. So, okay, let's close. Okay, now I wanted to measure the voltage across the Zener. I want to calculate the current that passed through the series resistance that we developed. And you can see that in the calibrated values, we don't have 212 ohm that we calculated. So I choose 215, which is the closest one to the 212. And I add a load of 1 kilo ohm potentiometer as a load across the Zener diode. I put the voltmeter to measure the voltage across the diode. I put the ammeter to measure the current going through the resistor, and I also put the power meter to calculate the power consumption, power that is consumed by this Zener diode. Now, I also set the voltage at 10 volt as we had in our exercise. Now, if I click run, you can see that the current passing through this resistor is 24.8 milliampere, which is below the 25 milliampere that we are aiming. The voltage across the Zener diode is a 4.67, which is very close to 4.7 theoretical value that we had. And you can see that this diode consumes 72.2 milliwatt of power. Now, let's change the load. I wanted to change to 80% load. As you can see, the current here exceeds, let me show you. This is the 50%, the 30%. As we rising the value, okay, the current is gonna go lower, so it's now 24.8. The value of the voltage across the Zener diode is still the same, but the power consumption is gonna be increasing. Now, what's happening is that the excess of the current, the Zener diode would absorb that excessive current. Okay, so it could keep the voltage across the terminal equal. So let me go toward like 50. Now you can see if the load is increased or milliamp is decreased or increased, which is right now passing the value that we aimed for. So probably the 215 is not safe enough. So we need to apply a safety factor, like for example, like 5 or 10 to make sure we are good. Don't do 10 because we are gonna fall below the I mean. You have to choose the a scaling factor for the safe resistance in a way that we are between the minimum current and maximum current. The voltage now, because of this excessive amount of current, is deviated from the value that we expected, and we have a lower power consumption, and it's because of the deviation in the voltage. Now, as you can see, the change in a load basically changed the value of our power consumption, our voltage across the our current consuming from the source, but the voltage was pretty much stable. Now, if we change the value, let me stop the simulation. If we change the value, for example, we do it like a 9 volt, so there is a deviation in source, and we run the value, you still see that the voltage across the Zener is consistent. Now, the current and power would change and is reasonable because of the KVL and Ohm law. Now let's go over voltage. It was 10. Now let's go to 12, for example. And we are gonna do run, and you still see the voltage across the Zener diode is still in the same range of 4.7 volts. So whatever happened in the source or the load, the Zener diode, if it's happened to fall between the minimum current and maximum current, okay, it would keep the voltage stable. Okay, so that's the basically the expectation that we had based on our calculation, and you see that this is going to happen actually in the simulation too. Now let's go toward the actual experiment in lab.
Okay, let's go through the actual test in the lab. As you can see, let me disconnect these. As you can see, I already built the circuit that we had. Now, I didn't have 212 or like 200 and around 212 resistors, so I used two 470 ohm resistor in parallel. So basically, I created a 200 and around 235 ohm of resistor in series with my source. Now it's connected in series with the source, and after that, the cathode of a Zener diode is connected to the resistor, and the anode is to the negative terminal of the source. And then we place the potentiometer as a load exactly across the diode. Okay, now we are going to first test the voltage across the diode and see by the change of our load how much the voltage would change. Please do not get disconnected. Okay, now I'm going to put the voltmeter in the DC volt. Okay, now I'm gonna apply the 10 volt voltage. Let me show you this, the 10 volt voltage. Okay, so you can see that right now with the initial value of the load, my value for the voltage across the diode is 4.69, which is extremely close to the theory. So we are very good at the voltage across the diode. Now I'm going to change the value of the load. See, I am changing the value, but the voltage across the diode would change, but still is very close to 4.7. Okay, so no matter how much I change it, it is still very close to 4.7. So the circuit working quite good. It keeps the value of our voltage pretty consistent. Okay. Now, I'm going to change the voltage source. For example, I'm going to go to 12. And you still see it's still around 4.7. It's a little bit higher than before, but it's still around 4.7. So it's pretty much regulated. And I'm going to go lower than 10, like 9, and still it's 4.6. So the voltage regulation works pretty good. Now let's go back to the 10 again. Now, the next part is that we wanted to see how much current goes through the circuit. Okay, now keep the voltage in mind. So it's 4.67 volt across the diode, because for the power consumption, we are going to need that later on. Now, disconnect the source. In order to calculate the current that goes through those resistors, I need to put the current meter in series with my resistor. So let me, get a jumper cable, and I'm expecting a milliamp, so I'm gonna put this probe at milliamp and put the multimeter at milliamp. Value is still AC. Be careful, I'm gonna change it to DC. Now I am gonna connect my ammeter in series with my resistor and try to apply the voltage. Now, you can see it's 9 milliamp, which is way below the value of I max. Okay, but it's still above the I mean. Okay, now why is that? Because I changed the value of the resistor, so it's not exactly what we calculated in our circuit. Okay, and there are some errors that you know already about it. So this is our value. Let's change the load and see what's going to happen in our value of the current. So I am going to change the load to the 0. Oh, we succeed. So we still need to make it higher. So practically that 212 is not properly tuned and is not safe. We need to have like a scaling factor to get over all the errors in our circuit. So the Zener diode is not exactly what it should be in theory. The resistance are not the same. The potentiometer is not the same. So we need to apply a little bit of correction factor to make sure we are not exceeding the value of our maximum current. So you can see that when I change the value of the load, the current would change, but we see that the voltage is still gonna be the same, around 4.7 volt. Now we also wanted to see how much power is consumed by our diode. So to do that, we are gonna put our diode in series with the ammeter. So I'm gonna connect the diode somewhere else. So I'm gonna connect the prop here and here. So now ammeter in series with our value. Now we saw that our power is in a amp values. Sorry, in milliwatt values. Okay, our voltage across the diode is 4.7, around 4.7. So that means our current should be also in a milliamp value. Okay, so we are in a milliamp DC current, and we are going to apply the something. Okay, you can see that current is 9.65 milliamp. Now, if we multiply that by the voltage that we had, let's do that. So we have 9.65 milliamp times 4.68 voltage that we calculated before, we measured before for the DC voltage across the diode. Okay, it is gonna be, this is not right. 0.956966, sorry, times 4.6 volt, and it's gonna be 444 milliwatt, which is close to calculation that we have, which is 500 milliwatt. Okay, so as you can see, our circuit, our calculation, our simulation, and our measurement in a lab is pretty much close to each other. There are errors, and this is because of the reality. We are not living in an ideal world. So this is going to be an error. You can calculate the error. But I suggest you, because we already covered the uncertainty principle, I suggest you to actually run the measurement for at least 10 times, okay? So you can actually calculate what is the uncertainty of your measurement. That way you can see the effect of that error way better than just comparing the measurement and the simulation and the calculation. Okay, thank you very much.